All right. So any questions before the proof? Any questions other than why is this true? Okay. And let's go. I'm going to make my life and your life a little easier with a couple of unimportant but convenient assumptions. So I'm going to assume our base case is simply t of 1 equal 1. It doesn't matter. I encourage you to go back through the proof later and verify that it doesn't matter. As long as it's sort of constant time below some constant size input, it's fine. And then we're told that t of n is bounded above by a times t of n over b. I'm just going to go ahead and write out the hidden constant in the big O notation. So c times n to the d. And also, I'm going to assume that n is a power of b. Okay. Again, this is not an important assumption. This conclusion remains correct in general, but this will allow us to focus on the main ideas about why the master method is true. Okay, so the general case is similar. It is, however, more tedious, and in my opinion, not a good use of the scarce resource known as 161 lecture time. What we're going to do is we're going to follow the pattern of the merge sort analysis and see what happens. The merge sort analysis, you'll recall, the key idea was to use a recursion tree. Why use a recursion tree? Because it lays out the total work performed by all of the various recursive calls in a way that it's easy to add up. Okay, and the way it's easy to add up is level by level of the recursion tree. Okay, so we're going to do that again, but now with these generic parameters a, b, and d. So we have our level 0, which is the outermost call. How many children does this node have? What's the branching factor of this tree? A. It has a child for each recursive subcall. And there are A recursive calls. So at level 1, what is the size of the input? N over B. By definition, right? What does B mean? Like, look at the recurrence, right? So by definition, you have A recursive calls, and each one operates on an input of size of 1 over B fraction of what you started with. Okay? Previously, A and B were the same thing. A and B were both 2 on Thursday, but remember they're not the same thing now. Conceptually, their meanings are distinct. One is how many, and you already see this in integer multiplication, right? So in integer multiplication, say the first algorithm, we recursed 4 times, but each time it wasn't a quarter of the input, it was a full half of the input. So some of the input was being passed to more than one of the recursive calls. Okay, so we're no longer necessarily splitting the input evenly between the recursive calls, like we did in merge sort. So now these again will have A branches. And once again, eventually we'll terminate at the base cases. Okay? base cases which have size 1. And what is the level down here?
Log base B.
Log base b of n. So remember the meaning of log base b of n? That's how many times you cut n by a factor b until you get down to 1. We started with n at the top. We stop when we get down to 1. Right, so by definition of log, it's log base b of n times. Okay? So that's our recursion tree. Why did I write decision tree? That. Didn't mean to like switch to 121 on you there. Recursion tree. Okay, any questions?